We have previously discussed that energy moves through an ecosystem, but nutrients have to be recycled. I want to spend a little bit more time thinking about the energy moving through an ecosystem and how it moves between individuals in particular. So we know that the sun provides the energy to almost every ecosystem on this planet, directly or indirectly. So what we have to think about is how life takes that energy indirectly or directly from the sun and converts it into something that's usable for us. We know about producers, we know about consumers, or autotrophs and heterotrophs, but what we want to focus on today is actually how they move energy between individuals. So something known as a trophic level, or some folks refer to it as a feeding level. When we talk about these levels, what we look at is starting with the sun always. Just because you cannot get energy from the sun directly doesn't mean you're not getting it indirectly, right? So what we see is this interaction of organisms between these feeding levels or trophic levels. So we start with our autotrophs, so they're going to use the sun directly. And then when we look at primary consumers, such as the snail here, the primary consumers are going to eat the autotrophs. The secondary consumers are going to eat the primary consumers and potentially the autotrophs. The tertiary consumers eat the secondary consumers and potentially the primary consumers and potentially the autotrophs. So we get this leveling interaction kind of hierarchy associated with feeding. Now, if we put it side by side with kind of a terrestrial system here, you can see these top level consumers are what we refer to as quaternary consumers. You can go higher than this. We don't see it very often because to be a quaternary consumer, it means you have to have all of these levels below you. You have to have, in this case, our whale eating our tuna, the tuna eating the herring eating the zooplankton eating the phytoplankton, in essence, eating sunlight, right? So these kinds of interactions at this high level are actually very difficult to find, and most of the time we don't look at a straight line approach like this. Often we look more at a food web, so there are lots of interactions. They've color-coded things here for you so you can see the difference between the levels of consumers, and you see that if we take our primary consumers, an owl can be a primary consumer. Okay? This seems kind of odd, right? But it all depends how they get their energy and where things are coming from. So if you follow the lines through, we've got our autotrophs at the bottom that feed the primary consumers, of course. And the primary consumers are feeding the secondary consumers, and this whole sequence of events that are going on. So depending on the organism, just because it's a heterotroph doesn't mean that it's what we would consider a top-level heterotroph. We can certainly have all kinds of intermediates, and you definitely eat between food levels. Think about what you eat in a day and whether or not that would make you a primary, secondary, or tertiary consumer, or in some cases, I suppose, quaternary. We also have to deal with the fact that things die, things leave waste, and have to be broken down. So we are completely dependent on this very special class of consumers known as detritivores. Okay? Now, in our detritivores, we have organisms that may be eating lots of dead things, right, like our decomposers, but we also look at the idea of these detritivores potentially working on organisms that are not dead yet. Okay, so when we look at something like a fungus, they may not necessarily be working on something that's dead, right? They may be living on something that's alive. But most of the time, what we're most interested in is looking at this recycling and having the nutrients return to the soil. So we're dependent on them breaking down this waste, breaking down byproducts, breaking down anything that a living organism discards. Okay, so we've got all these things that we have to consider. So we've looked at this chart before, thinking about competition and interactions and so on. But now when you apply it to our energy models and our ecosystem models, what we have to think about is things like, why are there so few big, fierce animals? Why? Well, when we look at energy transfer, it turns out that only about 2% of the sunlight that reaches the surface of our planet gets converted or assimilated into what we call gross primary production. So essentially builds plants. Okay? So a lot of it, is lost as heat. A lot of it, is used in cell respiration. Plants still do cell respiration. They have mitochondria. They have to grow. So they're doing that cell respiration. And what we want to look at is this net primary production. This is what's most interesting to us, because this is what is actually going to be built into biomass that we've talked about before, or basic plant materials. So we've got our gross primary production, that 2% of the sunlight that's coming in. So if we say that's 100% of what is available, right? And then essentially we're going to tax it. We're going to lose some as heat. We're going to lose some as cell respiration. But what is left, this biomass or the net primary production, we label it NPP, we actually see that as being available to primary consumers. So you can think about this sort of like your paycheck, right? So you have your annual salary. That's what we call your gross income. But after you pay into Social Security, into state taxes, into local taxes, into school taxes, into your benefits, into your retirement, into your medical care, in the end, your net income is what actually goes into your bank account, right? Okay, so this works the same way with plants. What we're interested in is this end, this net that we have available, because our caterpillar can't eat that tax. It eats instead that net availability or net biomass in our plants. So when we look at our caterpillar, though, he's not very efficient either. He uses about 15% of that plant material for growth, a third of it for cell respiration, and the rest of it gets eliminated in his feces. Okay? So if we assume he takes in roughly 100 kilocalories, remember this is 100 calories with a big C on your food labels, right? So if he takes in 100 calories of leaf, he's going to use about a third of that for cell respiration. Half of it he loses as waste, and then about 15% of it roughly will go on to growth. So, but then something eats the caterpillar, right? Well, what's available in the caterpillar? Only that roughly 15% in some cases for efficient consumers. Others, we look typically at a 2 to 10% movement of energy between these levels. This isn't very good, right? So if we look at only having 10% or less of the energy available, so if this is our 100% line, and this is net, right? So this is what the plant has actually put into its growth. If that's 100%, our primary consumer only has 10%. Our secondary consumer has 1%. Our tertiary consumer has 0.1%. So when I asked you why there aren't very many big, fierce consumers, this is why. There just simply isn't enough energy left to sustain them. When we look worldwide at what we call primary production, what's available? What's the average net primary production? What's biomass? What's available, right? If we look at our graph here, the best availability of net primary productivity or plants available for consumers is actually in algae beds and coral reefs. Tropical rainforests, yeah, close second. But then we get into estuaries. We'll talk about these with ecosystems. Very, very highly productive systems. Temperate deciduous forests like we see in the Northeast, and then into the others as well. Might not surprise you that desert doesn't have a lot of primary productivity, but neither does the open ocean. They're essentially equivalent in their lack of availability of energy for the next consumer levels.